Hang on, Sidney Crosby's playing his 1000th game. I have to take a little pause. Yeah, okay, I'm multitasking. Sorry about that. Sidney's 33. Oh my gosh, I'm getting so old. Anyhow, here is the first question, kind of a warm-up question about properties of addition and multiplication, which might sound easy but is kind of clunky. So the first question is, or the warm-up question is, can forces of 13 newtons, so that is physics, 37 newtons, and 16 newtons hold an object stationary? And the question is to explain. And the answer to this is no. Because what you have to do, and I'm going to draw a picture which is totally not to scale, which kind of breaks a rule. But if you draw a 13, wrong symbol. If you draw a 13 Newton vector, or a vector representing 13 newtons, then the 16 Newton should be to scale, but it should be longer than the 37 Newton. And the 37 Newton one is going to be more than double the 16. So there's me trying to do scale for this. And the deal is that, and it doesn't tell you direction, so I've just doodled 3 vectors here representing each of the newtons. But if you can take the 13 Newton, or one of the vectors, and add it to a second vector, so in this case, I've taken the 13 Newton vector and the 16 Newton vector, and I've added them together, that actually together makes 29 newtons, which, and remember, I am designating direction here, and of course that was just a super bad job. The 37 Newton force is more than 29 newtons. So I'm going to put it here. And because that is the case, this cannot hold, or these 3 combinations of forces cannot hold an object in one place, because 2 of them will not completely offset the third. And that's how you tell whether something can hold an object stationary. So the explanation is in the picture. It's also in a whole lot of words that I'm not really wanting to write down here. But the math doesn't let this happen. So now this list of properties, the not so fun looking properties. And you've got to be careful about how you write things. So I'm saying that before I disclose the slide. And it all comes from this. So our first, the title, properties of vector addition and scalar multiplication. So I have, in this list of 5 properties, I am having to talk about vector A, vector B, and vector C, and then I'm talking about just normal numbers, so scalars, and I've picked 2 of them, and the letters I've picked are K and M. I am going to guess that this is straight out of your textbook or a textbook. Please know that if you switch textbooks, this could be vector U, vector V, vector W, and this could be, I don't know, P and Q are scalars. So these things can change depending on the textbook, but more often than not, you'll need 3 vectors and you'll need 2 scalars. So these are directed line segments, and these are just plain old numbers. So we've looked at the first one already. It's actually got a name. Don't worry about memorizing the names, but the commutative property of vector addition means that if you decide that you're going to add 2 vectors in the opposite order, you will end up with an equal vector. And we've already done that. I think it was note number 2. The next one is the associative property of vector addition. So that's saying that if you take 2 vectors and add them together and then add a third one on, so finish off the first 2, then take that result and add a third one on, you can do that in any order. So you can take any of the 3 vectors, take 2 of them, add them together, and then add the third one on, whatever the third one left is, and you will end up with the exact same result. The next one is if you've got any vector and you multiply it by a scalar, and then take that result and multiply it by another scalar. That is the same thing as if you multiply the two scalars together, then apply it to the vector. And this is called the associative property of scalar multiplication. And then the last two are called distributive property of scalar multiplication. And it is that if you take two vectors and add them together, like we did with the A and B, or maybe it was U and V from the last node, and then take that and multiply it by a scalar. That is the same thing as if you multiply vector A by a scalar, multiply vector B by that very same scalar, then add them together. So the property that looks like a mini foil is actually in existence in this. Although you do have to be careful, like I said off the top, about what you are designating as vectors and what you are designating as scalars. So it doesn't work with vectors and vectors. It's a scalar and two vectors in this case. And then it kind of works a little bit backwards in that if you take two scalars and add them together and apply that scalar to a vector, it is the same thing as if you take each individual scalar, apply it to that very same vector, and then add them together afterwards. So these properties are useful in simplifying vector expressions. So when you get to do math that isn't necessarily the drawings, so it helps you with the algebra portion of it, for lack of a better way, because this stuff does work a little bit like algebra, which is lucky because most people dislike trigonometry and dislike logarithms because they don't work as algebraically as vectors do. So let's look at some questions. So the first one is, given that vector A is made up of 3 vector u's minus 5 vector v's, and vector B is equal to -2 of those very same vector u's plus 7 of those very same vector v's, determine how to construct 5 vector A's plus 4 vector B's from a vector u and v, and I haven't even told you what they look like. So here's the important part. You can do this pretending that it's algebra. But every time you put down a letter, you have to remember the arrows because we're not doing algebra. We're doing vectors. So let's see if I can do this without making any silly typos. I'm going to pick purple just for fun. So 5 vector A, I'm just going to write the question down again. So 5 vector A plus 4 vector B's, we're adding them together. So I can take 5 and I can find out what A is, and A apparently is 3 of these vector U's minus 5 of these vector V's. Oh, I'm going to sneeze. Maybe not. Oh, yes, I am. Excuse me. Oh, one more. Excuse me. Oh, I wish I could stop those. Then, plus 4. And here's B. B is made up of this. And because of all these properties, it lets us, in the first case, take the scalar and apply it to the vector, even though another scalar is there. So we can do this. So I can multiply the 5, just like algebra, through here, and I can multiply the 4, just like algebra, through here. So that's 15 vector u's minus 25 vector v's minus 8 vector u's plus 28 vector v's. Now I'm going to do a line that's unnecessary, but it's true because of the order not mattering. But here's my u's at the front, vector u's, and here's my vector v's at the back. And then I can do algebra, but it's really with vectors. So it's actually using these properties, which I don't need you to memorize. So that's 7 vector u plus 3 vector v's. And that's your answer. Now, if there's a question in your mind, and I don't know if I can do this really well, but if there's a question in your mind of, oh, well, if I take off all these little vector symbols and then remember to put it on in the end, is that okay? And the answer to that is no, stop being so lazy. It's all vectors. It's not vectors at the beginning, non-vector, 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 vectors. It's vectors all the way through. You have to put that vector sign on the entire way through this question. And if that's not what you want to do, then I do not want to go over the bridge you build for me. So you've got to be extra careful when you're doing vectors. So don't take the lazy route. Thank you. All right, next question. This. And this is kind of a redo from the last note. So some of these I'm not even going to use the picture for, but I've got a picture to represent this, and we can check it if you like. Let's do the first one with the yellow pen. So D to A, first of all, and then A to B. So the answer for this question, and I'm just going to alternate colors all the way through. The answer for this question is we started at D and ended up with B. And like I said, as long as you have a plus sign and these match, that actually works. So I didn't have to go through all of this. That's not lazy. That's using the properties of vectors, as opposed to just leaving off symbols because you don't feel like writing them. Let's do it again. C to B, then B to A. So the shortcut is C to A. Let's see if that works, because I do have the plus sign, and my B's do a little matching game, so I start with C and I end with A. That totally works. All right, next one. Oh, this isn't working. It's not a plus sign in the next one. So this says D to A, and then it says B to A, but backwards, because it's got the negative. So the answer to this question should be D to B, just like question A, because that's our shortcut after we've made the motions. So let's see if it actually works when I use the properties of vectors. So what I can do, and yeah, you got to show your work, is I'm going to leave this one the way it is because it's positive and it's all good. So I am going to turn this into A to B, which means it's the backwards of this. So the negative from that cancels with the negative from this, and you end up with a plus sign. And plus signs with matching letters let you start with this one, end with that one, and you do get that answer. So it works out beautifully. All right, so I'm not going to look at the picture yet for this question, and I'm going to see if I can do what I just pulled off. I'm going to dig out the red pen. So I like this one. It's positive. I also like C to B. It's positive. So this one and this one are all good in my mind. This one has a negative in front. I don't like that. I am going to reverse it, which means reversing that. That's got a negative, so I'm going to reverse the letters and reverse the sign. And I've got plus signs, so I'm extra happy now. The thing is, these don't match, these don't match, these do match. So I'm going to see if I can do a little rearrangement, which is actually the properties of vectors, so that I can actually pull off this. So D to C, that one's taken care of, plus C to B, so these match over the plus sign, plus B to A, these are all vectors, over a plus sign. Then the last one, which is this one, I haven't dealt with it yet, A to D matches over a plus sign. So I started with this letter and I ended with this letter. So if I'm not thinking about it, that's D to D. So let's see what that looks like up here in the picture before I tell you that there's one more line. So let's leave it at this. So D to C, D to A, but backwards, C to B, and A to B, but backwards. So if I start at D, which is where the question says to start, I can go along here, I can go along here, I can go along here, and I end up there. So it provides a perfect track for this, which is great, and it does tell us that we're going from D all the way back to D. But in vector language, that means we went nowhere, in which case you get to say that it's the zero vector, and that's where the zero vector comes in. Okay, so I'm going to disclose the next one, talk about it a bit, but then take a hand cramp break because this was actually quite difficult for my hand to take care of. So here's the next picture. This is why you have blank notes. So example, given parallelepiped A, B, C, D, E, F, G, H, state a single vector equivalent to each of these six. So I'm kind of hoping that I made them movable, which is nice. So a parallelepiped is a six-faced solid, so it's like a box, with every face being a parallelogram. So it doesn't necessarily have to be your perfect upright box. It can be a super slanty box. But it means that this is a parallelogram at the front, it's a parallelogram at the back, it's a parallelogram at the side, it's a parallelogram here, and it's a parallelogram at the bottom, and it's a parallelogram at the top. Okay, so this is tough to see. That's the only thing with this. And like I said, it is called a parallelepiped. I did not make up that name. I am not that smart or that difficult. So here are the questions. Can't move that one. Can't move this very well. And I'm just going to pause it. We're looking for a single vector equivalent, so we're looking to do exactly the same things we did here. And I will be with you after my hand cramp goes away. Oh, this is a longer one. All right, are you ready to have your mind blown? So you can't do the little, I don't know, swoopy happy face thing with these questions because there's no repeating letters anywhere in this, regardless of if you turn this around. So this is as much of a visual problem as it is a mathematical problem. So I'm going to scribble all over this in yellow. I'm going to increase my eraser because that little eraser was kind of getting to me. And I'm going to show you how to do these questions. So A to B is this. No big deal. And C to G is this. No big deal. They aren't even attached. So what you have to do is realize that you are allowed to move these vectors around as long as you maintain their direction and their length. So AB, for instance, is the exact same thing as D to C. It's the exact same thing as H to G. It's the exact same thing as E to F. I'm going to leave it there because that's the way my brain works. C to G is the exact same thing as D to H. It's the exact same thing as A to E. It's the exact same thing as B to F. I'm going to leave it there. And then I'm going to say, okay, you know what? I like that. So I've just shifted its letter components, but I've kept the length and the direction of this vector exactly the same. And that means that I can answer this question with this is the exact same thing as A to F. Now I hope you realize there's another answer to this. Because if I pick up A to F, I can place it at the back, and that's the same thing as D to G. So what that means is that I chose to take C to G and move it forward to its equivalent vector. But I could have taken A to B and moved it back to its equivalent vector and got D to G, which is the exact same thing. So that's what makes this stuff difficult. I have to have a lot of answers to match yours. Now, in this case, there's only 2. It's not that big a deal. So I'm going to erase this, and we start again with the next one. So I'm going to dig out yellow again. A to F. A to F is diagonally through this face, which is tough to see. So if you need, in a test situation, some sort of, I don't know, I usually hand people a Kleenex box with this, not because they need Kleenex because they're going to cry, but because a Kleenex box is a parallelepiped. It just happens to be a completely 90 parallelepiped. But there's A to F, diagonally through the front face. Technically, A to F is diagonally through the back face as well, but it's D to G back there. Not that it matters. That's where I see it right now. And then I have to go C to B. So C to B is here. Notice I drew it from C to B, but because it's got a negative, I have to reverse it. And C to B could be anywhere else. It could be this one. That's not helpful. That's tail to tail. That's not helpful. It's nowhere near the first vector. This is helpful. So now I've gone A to F and then F to G. So A to F, and then I've gone F to G with my replacements. Over a plus sign, these match. My answer visually and algebraically, or vectorly, I don't know if there's a word for that, is start at A, go to G. So there is an answer. An answer. So what I've done is I've made this so that I can group it together. And the reason I did that is so that I can move it out of the way and we can work on another one without me having to scroll too badly. So I'm going to do the next ones next. Yeesh. 3 of them. So I'm just going to alternate colors just for fun. So I'm going to do these ones in red, still with yellow. A to H. A to H is diagonally through this side. B to A is that, but it's negative B to A, so I'm going to put my arrowhead here. And then F to B, positive, is there. So I'm going to leave this diagonal guy where it is, and I'm going to take my A to B, or my negative B to A, and I'm going to move it across here and then up. So this length is the same as this length, is the same as this length, is the same as this length, and direction. So before I move anything else into place, I'm going to say, okay, I liked AH, A to H, and then negative B to A is the same thing as positive H to G, and then F to B is the same thing here, and that's useful because that tip to tails everything there. This isn't. That is probably where I'm going to leave it because now I can follow this one tip to tail with this one, tip to tail with this one. And just so that I have a nice little solution, I moved F to B to its equivalent G to C. Don't get lazy with the vector symbol. Yes, I'm talking to myself. Over a plus sign, matched, over a plus sign, matched. We started at A and we ended at C. And you can see that here. So it's just the shortcut. And I say just, and this is not easy, especially if you are like me and you're not horribly visually gifted. And I don't mean my eyesight sucks. I mean, you have to be able to see in 3 dimensions. That is tough stuff. All right, next one. Yellow. A to E. Whew, that one's not so bad. It's not diagonal or anything. And C to B. Forwards. Lots of possibilities. So as long as you move things tip to tail, so you could move that to here. Those are the same things. Or you could move this one here. That's tip to tail. So I'm going to leave it there. So that means that this thing is the exact same thing as C to B added to B to F. That's lousy. And so the answer, algebraically or vectorly, is C to F. Can we see that in the picture? Start at C, end at F. Yes, we can see that in the picture. So group this together. Pull it out of the way. And pull in our last one. All right. Oh my gosh, I'm not even going to do this one with the picture. Plus sign, matching letters. I'm excited. Whoa, I'm excited, except I can't work my pen. Start with A, end up with C. If you want to track it through, you can. Let's do it just for kicks. A to G, diagonally through the whole box. G to C. A to C is the shortcut. Yes, it is. So you have two ways of doing this when you have a picture. All right, last one. Last one of the note. Yellow. A to F. This one doesn't have the match and deals. So diagonally through this face. B to C, but backwards. G to H, forwards. Huh. Can you arrange them? So this is like a puzzle. So I'm going to see what happens when I take this line, which is going diagonally through this face at the front, and I'm going to move it diagonally to the face at the back, which is the same thing, and then I'm tip to tail here. And this one, I can move up to here. Tip to tail, tip to tail. Hey, that works. So it's just a matter of messing with it. So I've started here after all of that, ended here. So my answer for this is I started at D and I ended at E and I made a vector. And that is all. Because D to E is there, that means there was another answer that we could have gotten with different movements, which would have been C to F. So I actually have to have both of those written down in the solutions. All right, so that is the note. This is the suggested questions, which are on the Google site. Google site is right here. I've already updated. I've done 3 notes today. Holy smokes. It's only because it's dark outside right now. It was a very nice day. So, introduction to geometric vectors. I haven't added on the video yet because I still have to convert it. Blank note sheet for homework. Addition and subtraction of vectors. Blank note video. Suggested questions here from the red textbook. Properties of vectors just finished. Suggested questions as listed back there. Blank note. So remember, you don't have to draw the pictures. They're there for you. So how many notes do I have left here? 1, 2, 3, 4. 4 of them. I've done well today. Yay me. All right. So good luck with that. Ask questions. Records being broken all the time.